Remember the mean, median, and mode from math class? They're etched into my brain from 4th grade. The mean is the average, the median is the middle value, and the mode is the most common value. But in this video, I'll show you what they don't teach elementary schoolers. A fast and beautifully clever way to find medians, which involves taking the median of medians of certain values and uses a surprising sort of magic number to make it all work. Now, to motivate why we'd even need a fancy algorithm, compare the task of finding the median to finding the mean or the mode. How would you find the mean of these numbers? You would probably just add them up one by one and then divide by the length of the list. How about the mode? Well, you can just go through the list one number at a time, count how many times you see each different number, and keep track of the maximum count. But the median is the middle value. To calculate it, you have to consider how the numbers compare to each other. And it seems like the best method is to first sort the list and then count to the middle number of the sorted list. Back in elementary school, finding the median always felt slower than finding the mean or the mode. And while I'd like to say the thought pushed me to investigate why that was the case, in reality, I probably just finished my worksheets and counted the minutes until recess. But there really is something deeper going on here, and that's what we'll explore in this video, coming up shortly. Speaking of doing in-depth analysis to understand a subject, this video is sponsored by Ground News. Now, I chose to partner with Ground News because I'm honestly just a super big believer in their website. They show you how the same news stories are covered by different sources. For example, in July, DeepMind and OpenAI boasted new AI models that reached gold medal performance at the International Math Olympiad. But there are details that you wouldn't get from just one headline. For instance, there were still some competitors that outperformed the AI models. Gold medals are awarded to a top fraction of participants, so even though the AIs won gold, some humans scored even higher. Something else important is these models were general-purpose reasoning models. Interesting, a year earlier, Google's Alpha Geometry model only achieved a silver medal performance on IMO geometry problems, despite being specifically trained for them. I love what Ground News is doing. In addition to the different headlines, you can see the bias and factuality of every source, and it's really enhanced my news experience. If you want that experience as well, scan this QR code or go to ground.news/purplemind to get 40% off their Vantage plan. Thanks so much to Ground News for sponsoring this video, and now let's get back to medians. In elementary school, I always noticed that finding the median felt harder than finding the mean or the mode, and there's something to that. Specifically, finding the mean or the mode only requires scanning through the list once. If the total size of the list is n, the number of computational steps, or equivalently, the amount of time required to find the mean or the mode, is proportional to n. Computer scientists have a fancy way of quantifying this. We'd say the running time of these algorithms is big O of n, which means that there could be some extra constant factors or slower growing terms influencing the running time, but that as n gets large, as the input size gets really big, which is what computer scientists normally care about, the running time will grow in proportion to n. So big O of n means if you graph the running time versus n, it'll look roughly like a straight line. And finding the mean and the mode fall under this category. You could contrast O of n with O of n squared, for example, which will be relevant to us later. O of n squared running times look like parabolas, and take much more time than O of n as n gets large. Now, the way I learned, and the way most students probably learn to find the median, involves sorting the list, and sorting requires more work than O of n. It's sort of in between O of n and O of n squared, and we'll explore that in a bit. But the point is, if the first step of your median finding algorithm is to sort the list, it's going to be slower than O of n. However, I doubt they're teaching any elementary schoolers that you don't actually have to fully sort a list to find its median. And there is a way to find the median with an O of n running time, just like the mean and the mode. Or there are really two different ways I'm going to show you, with the second one especially being just utterly amazing. So how do these fast median finding algorithms work? Well, even though they do not fully sort the list, to understand them, we'll first need to learn about a particular fast sorting algorithm, since the concepts used in the median finding algorithms derive directly from this sorting algorithm. From there, we'll see how you can modify the sorting algorithm to become a faster median finding algorithm. Finally, we'll see how you can modify that algorithm to create a new one that achieves an extra special property. And to be fully transparent, this algorithm doesn't really see much use in practice, if any, but the way it works makes use of a sort of magic number, and it's honestly just one of the coolest algorithms I've ever seen. So without further ado, let's dive in. The sorting algorithm we need to learn about is called Quicksort, published by computer scientist Tony Hoare in 1961. And the goal is to, quite straightforwardly, sort a list of numbers in ascending order. The first step of Quicksort is to randomly choose one of the numbers in the list to be the so-called pivot number. Here we landed on 6. Now what we're going to do is separate the rest of the numbers based on how they compare to the pivot number. Starting at the beginning of the list, 3 is less than 6, so we'll move 3 to the left. If a number is greater than the pivot, we'll move it to the right instead. We keep doing that for each number in the list besides the pivot. So eventually we end up with 3 parts, a left sublist, the pivot, and a right sublist. By the way, you'll notice here that all of the numbers in this list are different from each other, so everything was strictly less than or strictly greater than the pivot. This of course doesn't have to be the case, there could be duplicate numbers, but from here on out we're going to assume that all of the numbers are different for the sake of simplicity. At the end of the video, I'll address how you can make an easy adjustment to handle duplicates as well. So back to carrying out the algorithm, everything in the left sublist is less than the pivot, and everything in the right sublist is greater than the pivot, which means if the left and right sublists were both sorted, we could get the full sorted list by stitching together the left sublist, then the pivot, then the right sublist. So what we can do is recursively apply the same strategy to sort the left and right sublists. We randomly pick a new pivot from each and separate the numbers into further left and right sublists based on how they compare to the new pivot. And we keep doing that all the way down until all the lists only have one number each. Lists with one number are sorted by default, so at this point we can start piecing together all the recursive results, combining the left sublist, pivot, and right sublist at each step until we get back the full sorted list. So that's how Quicksort works, but how fast is it? Well, the expected running time of Quicksort is O of n times the logarithm of n. I'll explain why in just a moment, but notice that I said expected because the algorithm could take more or less time depending on the randomly chosen pivot numbers. Most pivots, like the first one we chose, will yield a pretty even split, but for others, like this one, there could be a lot more numbers on the left or on the right. That being said, there's a pretty intuitive reason for why the running time is O of n times the logarithm of n. Let's count up how many operations are performed at each step of the algorithm. At the very start, all we did was pick a pivot and then scan through the list once to separate the numbers into the left and right sublists. That means the total work done at this top level is just proportional to n, the length of the list. So we'll write it as c times n, where c is some constant. Okay, what about the next level? Here we're just doing the exact same thing as we did at the top level, but on both the left and right sublists. So we do an amount of work proportional to the combined length of those sublists. That combined length is n minus 1, since these sublists contain everything except the original pivot. But we can actually just pretend it's n for the sake of simplicity. For all intents and purposes, the total work done at the second level is also c times n. It's easy to continue this logic further down. The sublists at each level, up until the very last few levels, will have a combined length that's extremely close to n, contributing roughly c times n work. Now, how many levels are there? Well, here's where I'm going to make a bit of an imprecise argument for the sake of keeping things less convoluted. The argument is to say that, on average, the sizes of the left and right sublists as you go down will get cut in half at each level, since a randomly chosen pivot will be greater than half of the numbers on average and less than half of the numbers on average. Therefore, we can expect the total number of levels to be roughly the number of times you can divide n by 2 before you get down to lists with just one number, or in other words, log base 2 of n. So the combined work done by all the levels is the number of levels, which we're estimating at log base 2 of n, times the work done at each level, which we know is roughly c times n. And that suggests an overall running time of O of n times log base 2 of n. By the way, the base of the logarithm doesn't really matter inside the big O notation, because logarithms of any base are all the same up to a constant factor, and constant factors can be ignored since we only care about proportionality. So the notational convention is to simply write O of n log n, where the base of the logarithm is left ambiguous. Now, as I was saying before, this argument is slightly wrong. The problem is that it assumes the best case scenario, which is that the randomly chosen pivots will split the list in half at each step. This is not really true. As we saw, sometimes the pivots will give worse splits. The details of the correct analysis are a little more complicated and honestly a bit besides the point for this video, but what you should know is that even though the argument we just did is flawed, it is at least in the right spirit, and the real expected running time does in fact still work out to be O of n log n when you flesh out everything properly. It just takes a bit more nuance to get there. And it turns out that O of n log n is actually the fastest possible running time achievable for sorting a list of n numbers. There's a really cool proof of this fact that I may cover in another video. Let me know in the comments if that's something you'd like to see. But for now, let's get back to the main topic of this video. What does Quicksort have to do with finding medians? Of course, to find the median of a list, you could just use Quicksort to sort it, and then count to the middle number. But that would have an O of n log n running time, and the whole point of this video is there's a more efficient method. Instead, there's actually a very small modification you can make to Quicksort to turn it into a median finding algorithm with an O of n running time. This algorithm is called Quickselect, also developed by Tony Hoare, and it actually solves a slightly broader problem than finding medians. In general, Quickselect is used to find the kth smallest number in the list for some number k. The median is really just a specific case of this. For example, in this list with 5 numbers, the median would be the third smallest number, which in this case is 6. So the input to Quickselect is a list of numbers, just like Quicksort, but in addition there's another number k, and the goal is to output the kth smallest number of the list. The first few steps of Quickselect are exactly the same as Quicksort. You pick a random pivot from the list, and then separate the remaining numbers into 2 groups, those less than the pivot and those greater than the pivot. Now in this example, there are 9 total numbers in the list, which means the median is the 5th smallest number. There will be 4 smaller numbers and 4 larger numbers, so k equals 5. But look at the left sublist. It contains more than 5 numbers. Since we know that everything in the left sublist is less than the pivot and everything on the right sublist, we now know that the 5th smallest number has to be in the left sublist. So we can just throw away the pivot and the right sublist and focus on finding the 5th smallest number of the left sublist. Now we continue as usual, picking a new pivot and breaking into further left and right sublists. And here we can see that the left sublist and pivot are 3 numbers in total, which we know are all smaller than everything in the right sublist. So the 5th smallest number is going to be the 2nd smallest number of the right sublist, since the 3 smallest numbers have now been removed, and 5 minus 3 is 2. When we once again break into further sublists, the left sublist just contains 1 number. So the 2nd smallest number must be the pivot itself. Now we're finally done. We've found the median of the original list, 42. In all of these iterations, we only have to do one recursive use of Quickselect, either for the left sublist or the right sublist, whereas with Quicksort we had to do both. Because of this, Quickselect is faster than Quicksort. How much faster? Well, if we do the same kind of intuitive but slightly flawed analysis we did for Quicksort, we can still estimate that the sizes of the left and right sublists get cut roughly in half at each step. But now we're only keeping one of them, not both. So we could estimate the total work as c times n plus cn over 2 plus cn over 4, etc. for some finite number of terms until the blocks get down to a size of 1. This sum is known as a geometric series, and it can be proven that it's less than 2cn. And the thing we really care about here is that the number of operations performed is at most proportional to n, which we call O of n. This is better than the O of n log n running time for Quicksort. Again, this argument is not quite right because it assumes the pivots split the list perfectly at each step, which is overly optimistic. But when you do the proper analysis, the expected running time does in fact work out to be O of n. I remember being pretty awestruck when I learned about this for the first time, because I had always just assumed that to find the median, you'd need to fully sort the list. However, not only is this not the case, but the way around it involves broadening the scope of the problem to a more general version. That is, to find the kth smallest number for variable values of k. This phenomenon of solving a problem by viewing it as a specific instance of a more general task is pretty counterintuitive, yet it actually shows up a surprising amount in algorithm design, which I find pretty cool. But anyway, let's recap where we are. We have an O of n algorithm for finding the median, or in general the kth smallest number, whereas for sorting we had the slightly less efficient O of n log n algorithm. But as we know, these running times are not actually guaranteed, they're just expected. The performance depends on the randomly chosen pivots. Most of the time, the pivots will split the list fairly evenly, like we supposed in our informal analysis, and everything will work out great. But if you happened to get unlucky and somehow pick really bad pivots, the running time would suffer dramatically. The most extreme version of this would be that you always happen to pick the minimum or maximum number in the list, causing all of the numbers besides the pivot to end up in the same sublist. Then the sizes of the lists would only decrease by 1 at each step, meaning the total work would be proportional to n plus n minus 1 plus n minus 2, etc., down to 1. It can be proven that this sum equals n times n plus 1 over 2, which grows proportionally to n squared. And this could happen in either Quicksort or Quickselect, so the worst case running times of both of these algorithms are O of n squared. That's much worse than O of n, and also much worse than O of n log n. Now, it's exceedingly unlikely that this would actually happen with randomly chosen pivots, but it begs the question of whether there could be deterministic algorithms for the same task. That is, algorithms that do not use any randomness whatsoever. When Quicksort and Quickselect were published, we actually did already have deterministic algorithms for sorting, such as merge sort, that run in O of n log n time no matter what, even in the worst case. The reason why Quicksort is sometimes preferred over deterministic sorting algorithms is because in its most optimized form, it uses less memory, which is often an important factor in addition to time. But it wasn't until over 10 years after Quickselect was developed that we would find a deterministic version, which is the main topic of the rest of the video. The deterministic version was discovered by Manuel Blum, Robert Floyd, Von Pratt, Ron Rivest, and Robert Tarjan in 1973. And it took over 10 years and 5 of the world's leading computer scientists to create it because, well, the algorithm is just really sneaky, and it fits together in a quite beautifully unexpected way, with the help of a magic number I've been referencing. So let's see how deterministic median finding works. Here's the key idea. Remember how the quality of our pivot affects the performance of Quickselect? Ideally, we'd want to pick a number for the pivot that splits the list into 2 equally sized halves, meaning half of the numbers should be less than the pivot, and half should be greater. So why don't we just pick the number in the list with this property? Well, wait a minute. That number is, by definition, the median of the list, which is exactly what we're trying to find in the first place. So we can't find the median to use as a pivot. Instead, there's a brilliant workaround called the median of medians approach to, without the use of any randomness, choose a pivot that is maybe not quite as good as the true median, but it'll be good enough to achieve all the properties we want. And as a little teaser, this is where the magic number comes in. But before we jump straight to that, it'll be worth it to walk through a couple examples of some initial attempts to make deterministic median finding work that come up a bit short, because it'll help us build up the techniques we eventually need to tackle the median of medians algorithm. And once we do get there, the extra context will help to appreciate why the magic number is so special. Okay, we know we can't use the exact median as a pivot. So the goal will be to somehow choose a pivot that will be close enough to the true median to sufficiently reduce the size of the list at each step. And remember, now we're trying to do this without any randomness. We have to come up with some completely deterministic method of finding good pivots. Let's use the pseudocode for Quickselect as a starting point. And since this is the first time I'm showing it on screen, feel free to pause the video here and make sure you understand what's going on. Now, the only thing we're going to change in this code is this line. Instead of picking a random pivot, we'll pick a pivot deterministically. Everything past that will remain exactly the same. So here's an idea. Imagine for a moment if we could use the median of just the first half of the list as the pivot. Not the median of the full list, just half. That median would be greater than half of those numbers, or 1/4 of the total numbers, and also less than half of those numbers, or 1/4 of the total numbers. Now think about what would happen if we did the rest of the Quickselect algorithm, but used this median of half of the numbers as the pivot instead of a random pivot. Since the pivot is greater than at least 1/4 of the numbers, and less than at least 1/4 of the numbers, the worst possible split ratio is 1/4 to 3/4. Definitely not as good as an even split, but at least it's pretty close. Now, this is great and all, but I said earlier that we couldn't just use the median of a list as a pivot, so surely we can't use the median of half of the list as a pivot either, right? Well, we actually can, and the way we do it is actually no stranger to us. We're already using it in the later part of the algorithm. To find the median of the first half of the list, we simply recursively apply the algorithm to the first half. As we know, finding the median is just a special case of the kth smallest number problem. And this works because half of the list is smaller than the full list. It's the same reason why we're allowed to recursively apply the algorithm to either the left sublist or the right sublist later. The sublists are always going to be smaller than the original list, which means all the subproblems will keep getting smaller and smaller until the lists only have one number, at which point the solution is trivial. A little side note here, the median of lists with an even length is defined as the average of the two middle values, but for the rest of the video, we'll redefine it to be the lower one of the two middle values. You could also choose the higher one, it really doesn't matter, but since we're using medians as pivots now, we need the term median to actually mean one of the numbers in the list. You really don't have to think about this too much, just know that when I say median now, it means a number that's as close to the middle as possible, slightly different from the conventional definition. Anyway, we've taken the median of half of the list to use as our pivot, and from here, the rest of the algorithm is exactly the same as Quickselect. We use the pivot to partition the list into left and right sublists, and then we recurse on the left sublist if it has at least k numbers. We recurse on the right sublist if the left sublist and pivot contain fewer than k numbers, or if the left sublist and pivot have exactly k numbers, we just directly output the pivot as the answer, since in this case we know the pivot is the kth smallest number. But does this method have an O of n running time? Let's see. The first thing we need to notice is that, like in Quicksort and Quickselect, all of the work done by the algorithm besides the recursion only takes a number of steps that is proportional to the size of the list. For example, creating the left and right sublists just requires scanning through the list once. And you can verify for yourself that everything else besides the recursive uses of the algorithm takes at most some constant amount of work per number in the list. So just like before, the total work done by the algorithm is proportional to the combined lengths of all subproblems produced during the recursive process. This means we can once again use our trusty block method to analyze how big the sizes of the subproblems are going to be at each step. As before, we'll represent the initial list with a block of size n. Now, there are two blocks that get created from this top level. One of size n over 2 to find the median of half of the list to use as the pivot, and then one more block for the main recursion on either the left sublist or the right sublist. We saw that the size of this block can be at most 3n over 4. And unlike before, these are the true worst case sizes of the blocks. There's no randomness involved now. We know for a fact that the blocks won't be bigger than this. Now, it's easy to continue the same logic for the next level. Each of those blocks also gets split into a block 1/2 the size and another block 3/4 the size. So really, each level of this block stack is 1/2 plus 3/4 or 5/4 the size of the level above it. But this is not good. Think for a moment just about the row of blocks that is about log base 2 of n levels down from the top. The size of each successive level compounds by 5/4. So the size of the log base 2 of nth row will be n times 5/4 to the log base 2 of n, which is n times n to the log base 2 of 5/4, or roughly n to the 1.32. We don't even have to bother counting up the rest of the levels in the stack. The work from just this one row is already proportional to n to the 1.32, which is not only worse than O of n, but it's even worse than O of n log n. We'd be better off just using the naive approach of sorting the list, which we know can be done with a running time of O of n log n. So what do we do? Well, as a second try, we could employ the same strategy, but maybe this time to choose the pivot, we'll only find the median of 1/3 of the list instead of half. But as you'll see if you do the analysis, you'd run into essentially the exact same problem. In fact, you can try choosing a pivot by taking the median of any proportion of the list, and the math will work out such that the running time is slower than O of n log n. I'll spare you those details here and instead leave figuring out why as a challenge to the viewers. But there's a genius tweak to this strategy that will make it much more efficient. The idea is to, instead of directly taking the median of some fraction of the original list to use as the pivot, take the median of several small subsets of the original list, and then take the median of those medians to use as the pivot. But one of the things that makes the final algorithm so tricky to discover is that even once you think of the right concept, it still doesn't quite work unless you figure out the quote-unquote magic number. So first, I'll show you that concept in a version that barely misses the mark, and then finally, we'll see how the slightest of changes somehow makes everything work out. The first step is to split the numbers into groups of 3. So you can imagine if each number is a dot, where smaller dots mean lesser numbers and bigger dots mean greater numbers, you could arrange them in a grid like this with 3 rows. Now we're going to sort each of the groups of 3 so that the lesser numbers are on the bottom and the greater ones are on top. Next, we'll get the median of each one, which will just be the dots in the middle row. Then we'll recursively find the median of those medians, similarly to how we were recursively finding the median of half of the list before. We'll use this median of medians as the pivot for the rest of the algorithm. Now, to see why this is better than what we had before, first let's revisualize the dots so that the groups with the lesser medians are on the left, and the groups with the greater medians are on the right. And to be clear, this is just a revisualization. Our algorithm won't actually sort the groups. But when viewed like this, the median of medians is in the center, since by definition it's greater than half of the other medians and less than half. More specifically, we can see that the median of medians is greater than 2/3 of the left half of numbers. It's greater than all the medians to the left of it, which are each greater than one of the numbers in their group of 3. So altogether, the median of medians is greater than 2/6 of the total numbers. Well, plus or minus a few, since this doesn't count the numbers in the middle group, and also there could be a partial group if n isn't a multiple of 3, but both of these facts become insignificant as n gets really large, which is what we're really interested in anyway. Now, similarly, the median of medians is less than 2/3 of the numbers on the right. It's less than all the medians to the right, which are each less than one of the numbers in their group of 3. So the median of medians is also less than 2/6 of the total numbers. Let's now repeat the analysis we did a few minutes ago to figure out the running time of this new algorithm. We've added an extra step at the beginning compared to last time, which is to create the groups of 3 and sort each one to find their medians. But crucially, the number of steps required to sort each group does not depend on the length of the list. They're always just groups of 3, so there's only a constant amount of extra work per group, which means all of the work done besides the recursive uses of the algorithm is still proportional to the size of the list. So we can once again use our block method to count up the total work of the algorithm. As always, we start with an initial block of size n, and there are still 2 subproblems created from the top level. One for the first recursive use of the algorithm to find the median of medians, and since there are n over 3 medians to take the median of, this block gets a size of n over 3. The second block is for the main recursion on the left sublist or the right sublist. And since we know the pivot is greater than 2/6 of the numbers and less than 2/6 of the numbers, the size of this block can be at most 4n over 6, or 2n over 3. And each of those blocks gets divided into a 1/3, 2/3 split, so the sizes of the rows actually stay the same this time. Similarly to all the examples we've done so far, since the sizes of the subproblems are shrinking by a constant factor at each level, the number of levels is proportional to log n. The rows are of size n, so the total work is O of n log n. Now, as a reminder, the goal was to get to a running time of O of n, so we're closer than we were before with the previous approach, but not quite there yet. The amazing thing is that the only modification we need to make to this algorithm for it to have an O of n running time is to, instead of splitting the list into groups of 3, split it into groups of 5. Yes, 5 of all possibilities is the magic number. To show you why, we're going to repeat everything we just did, but with groups of 5 instead of groups of 3. So we sort each of the groups and find their median. Then we find the median of those medians and use that as the pivot. We'll now revisualize the dots so that the medians of each column, shown in green, are sorted from left to right, and we can see that the median of medians is now greater than 3/5 of the numbers on the left, 3/10 of the numbers in total, and it's less than 3/5 of the numbers on the right, also 3/10 of the numbers in total. Now let's figure out the running time of this algorithm just like we did before. Again, there are 2 subproblems created. One to find the median of medians, and this time there are n over 5 medians to find the median of, so the size of this block is n over 5. And the second block is for the main recursion on the left sublist or the right sublist. Since the pivot is now greater than 3/10 of the numbers and less than 3/10 of the numbers, the left and right sublists could each be at most 7/10 of the numbers. So the size of this block is 7n over 10. Now look at how this time the sizes of the blocks in the second row add up to less than n. More specifically, they add up to 9/10 n. And the sizes of each row keep shrinking by a factor of 9/10 as they go down. Now, the combined work done from all the levels is proportional to n plus 9/10 n plus 9/10 squared n plus 9/10 cubed n, etc. This is a geometric series, and it can be proven that the sum is at most 10 times n. And so, the total work is, at last, just proportional to n. That's what we call O of n. Mission accomplished. We now have a fast running time, just like we did for Quickselect, but this time it's completely guaranteed, even in the worst case, whereas with Quickselect, O of n was just the expected running time. Now, we've gotten this far, and we could just end the video here, but there's still a little more to the story. Let's make a plot of the actual experimental running times of some different median finding methods we've discussed. So on the horizontal axis, we have n ranging up to 3000, and on the vertical axis, we have the time taken to find the median of a random list with n numbers on my computer, averaged over 100 trials. First, let's do the naive method we started with at the beginning of the video. Sort the list and then count to the middle number. In this test, I implemented Quicksort to do the sorting. Next, we have Quickselect, which we can see performs much better than Quicksort since the extra log factor is removed from the running time. Here's the Python code for those two, and for those of you curious from the beginning of the video, I'm putting a note on screen now about how these algorithms handle duplicate numbers, which we've been avoiding for the sake of simplicity. Now the final algorithm we're going to plot is the median of medians algorithm. You can see here that it also runs faster than Quicksort, but it actually runs slower than Quickselect. The reason for this is because the extra work to divide the list into groups of 5 and take the median of each one is more expensive than just picking the pivots randomly, which tends to be good enough to get fast performance. So what I said earlier about the values of the constants not really mattering is not entirely true. They don't matter for the sake of finding a big O bound, but because big O bounds ignore constant factors, they can often give off false perceptions of the real performance of certain algorithms. In truth, Quickselect is almost exclusively preferred to median of medians in practice because of the constant factor speedup, despite having a slower worst-case guarantee. But we can peek into that worst-case performance by counting something slightly different. What you're seeing here is a graph of how many times each of the algorithms compares two numbers in the list. So that could be for comparing a number to a pivot or sorting small groups of 5 for the median of medians method. The data on this plot is the worst recorded case out of 100 trials for each value of n. You can see for both Quicksort and Quickselect that there's quite a bit of variance in the number of comparisons, and that's due to the randomness of how the pivots are chosen. But for median of medians, there's a completely straight line upper bound on the number of comparisons, because it's deterministic. And every now and then, you do actually see the number of comparisons for Quickselect jump above that line due to really unlucky pivot choices. Now, it's pretty difficult to come up with any situation in which these fringe cases affect the running time enough for the median of medians algorithm to be preferred. After hours of searching on the internet, my conclusion is that such situations just don't really exist. Let me know in the comments if you find any evidence to the contrary. I'd love to hear about it. But in my opinion, fixating solely on this point is kind of missing the forest for the trees. For me, the moral of the story isn't just about median finding algorithms. It's that the realm of possibility in algorithm design is unfathomably rich. I mean, we started with a simple task of sorting a list of numbers, one of the oldest problems in computer science, and you'd think we'd have squeezed every last bit of insight out of it. But it was just a few small changes away from becoming a ridiculously beautiful algorithm, where we divide numbers into groups of 5 and find medians of medians. All of this is to say that you really shouldn't assume certain problems don't have sneakily clever solutions out there waiting to be found. To this point, I made a video previously on this channel that covers a story about a genius algorithm for multiplying big numbers faster than the way you were likely taught in school. And by the way, that one is actually widely used in practice. I'm sure you'd love watching that video since you made it to the end of this one. Thanks so much for watching, and I'll see you next time.